Hello students, so this is the numerical for the shaft. So the numerical is the layout of a transmission shaft carrying two pulleys B and C supported on bearings A and D is shown in figure. Okay, so here we have a shaft, right? So and this is supported upon two bearings A and D. Okay, these two are the bearings, and we have two pulleys here B and C. Here belts are there. Okay, I'll actually let me draw the figure. I'll draw it later once you start solving. Okay, so it is the question is, power is supplied to the shaft by means of vertical belt on the pulley B, okay, which is then transmitted to the pulley C carrying a horizontal belt. The maximum tension in the belt on the pulley B is 2.5 kilonewton. Okay, the angle of wrap for both the pulleys is 180 degree and the coefficient of friction is 0.24. The shaft is made of plain carbon steel and the factor of safety is 3. Determine the shaft diameter on strength basis. All dimensions are in millimeter. So here you see this setup is like this. Here we have a shaft, okay, and here we have two pulleys. One pulley is like this, okay, another pulley is there which is smaller in diameter. This is the, let me draw it again. So this is the shaft. One pulley is, this pulley is bigger in diameter, and this pulley is smaller than the this other pulley. So this is the shaft. Okay, now this is supported at two bearings here. These two parts, bearings, you know, bearings are the elements that allow free rotation, okay, and take its weight and the additional loads also. So these are the bearings. So bearings are, the point of the bearings are written as A and D, and these are the pulleys, pulley B and pulley C. Okay, fine. All right, so here you see we have belts like this. These are the belts. Okay, so here is one belt, okay, and this side we have the belt in some other plane in this direction. Okay, so in this manner, I think you can understand this. So these are the belts. Okay, belts are continuing. I mean this side, I mean it's kind of, this is the belt, and here we have another pulley like this. Okay, this is not shown in the question because this is not required. So this is the pulley. Here we have some motor or something, or some engine is there, okay, which is driving this thing. So this is being driven, this pulley is being driven by some motor. Okay, and I mean that will be written here somewhere. So vertical belt. Okay, power is supplied to the pulley B. It is written in the question. It is, so that's why this is pulley B. Power has been supplied by some external means. Okay, by some external means, and it is then transferred to this pulley, and from pulley C we will take it to somewhere else. Okay, so this shaft is used for transmission. Okay, so here you see since this motor is providing some torque, shall be some torque supplied to pulley B. This B is fixed to this shaft, so B will transfer the torque to this shaft here, and from the shaft it will go to pulley C, and from pulley C the torque will be transferred to this belt this side. Okay, so consider, see, you must understand that there are two planes. Okay, so this side you can take, like if you take the cross section of B, okay, or if you take a plane parallel to this belt, okay, belt, so parallel to, I mean plane parallel to belt, this belt, if you take, this is the plane. You understand? See, plane concept is important here, just like this. Okay, this is the plane. Understood? And there's another plane parallel to this belt. Okay, so that plane will be like this, horizontal. I mean this is the plane, this is the plane. Okay, you can understand, for which this plane is parallel to this belt. Okay, okay, fine. And this plane here, this plane here, like this, is parallel to this belt. Okay, parallel. So these are the planes, they are at 90 degrees. Okay, So this will be required later. I'll just tell you why it is required. Okay, now since torque has been supplied from to B, from B to C, torque is transferred. Now see, look here, in this belt we are actually delivering the power to some external maybe some there are anything we are connected, maybe compressor or something which needs some power. So from C it will take the power. That means it will resist the movement initially because it is it will have some inertia, that's why. So it is applying some torque, okay, and this part is resisting, okay. There will be some, then what will happen, this shaft here is getting twisted, okay, twisted, because B is trying to rotate it and C is trying to resist it, right? So there will be what, torsion, and from there we'll get the torsional moment here, torque T, okay. This is required, okay. This is one thing that we have to take into account because there is some torsion, okay. And you know, since there are, you can say, torsion also, okay, and one more thing will be there, okay. Look at this. See, you have actually studied about the belts, I think, and in theory of machines and kinematics of machines. So, and if you have not, you will actually you may just inform me. I'll just tell you. So here you see, belts have two sides, tight side and slack side, tight and slack, okay. Tight side is, will have some tensions, both side we have some tensions. Let me show you the belt tensions. So these are two pulleys, let's say, okay, and here they are at some distance apart. Now see, you need to provide friction to this belt, isn't it? Friction, sufficient friction has to be there, otherwise there will be slippage, okay. Belt will slip over the pulley, that will be a problem. So that's why what we do is we have to actually give some tensions. You can just think like you have a rubber band, suppose like this, okay. Rubber is there, hold it here in this I don't have a rubber right now, maybe this kind of string I have some, okay. This is the string, let's say, okay. This is connected, just think like this. So this is the pulley, okay. So here we are putting it here and here also. So if it is very loose, then what will happen, if this pulley rotates, this cannot transfer it, okay, because it is loose enough. So to make it tighter, okay, tight like this, and then it will create some friction between this surface and the belt surface, okay. That's why, since we are pulling it like this, okay, in this manner, so there will be some tension. Tensions are called, they are actually the reaction forces. So this is trying to pull and this is trying to pull in this direction, so they are being stretched a little bit. That's why these two will try to resist the movement, okay. Tension in this side, tension in this side. Now once you start rotating like this, okay, the one, let's say this is driving, okay, this is driving the other pulley, this is being driven pulley. So driving pulley, you can always consider that since it is rotating in this direction, the belt will move in this direction, right? Belt is going like this and will pass through, okay, this way. So this portion which is going into the pulley, okay, which is being pulled, this is called tight side. The tension will be more in the tight side and this slack side, okay. Slack side is, it is being pushed to the other part. So here power cannot be supplied because this is very flexible. We are trying to pull this part and that is pulling the other pulley. So this is tighter. This is called slack, okay. So tension here is more than, tight side tension is more than slack side always, okay. And let me just write this as P1, okay, and this is P2, okay. So this is P1 again. There are reactions only for this one also, for this one also. So P1, the tight side tension, P or T or whatever you want, or you can write T also, T1, T2. T means tension, okay. Here we are using P in this problem, so we are writing P1, P2, okay. So just take only one pulley now, because here I told you we have a driving pulley, okay, fine. This is driven pulley, but we do not need this part, okay. So we take only this part, okay, up to this, fine, okay. Now let's say this is tight side, okay, and this is slack side. So we have tensions P1, P2, which is all shown here, you see, Okay, so this is side view, this is the side view, this is the I can say shaft, and here we have a pulley, here we have a pulley, and this is, if you view from this side like this, then here pulley will be visible, bigger pulley, smaller pulley is there behind it, or you can just rotate a view from this side also. So the smaller pulley is visible, bigger pulley is behind it. So this is the smaller pulley, this is the bigger pulley. So I told you, see, this is P1, this is P2. Okay, now the concept you have understood, I think. So P1, P2. Okay, here we have P3, P4. Similarly, I mean, that is another pulley. So here also we have tight side, slack side. Let's say this side tight side is there, this side this slack side is there. Okay, so this is this P4, this is P3 is P4. P3, I mean, we just take 3 as greater than 4, so P3 as P4, I mean, for our convenience only. So one of them will be greater than the other, that's why P3 P4 in this manner, or you can show it in this direction also, for we didn't have any space, so that's why I have shown it that side. So this is P3 P4, understood? Okay, so they are in different plane. Now see, okay, what will happen due to this? You see, if suppose the pulleys have some load, this is not written, so since one more thing, the pulleys also, they will have some weight. Okay, their weights are there. All right, so what will happen? See, I told you have understood there will be a torsional failure. Okay, if I mean your shaft is not sufficiently strong, then there will be twisting and it will break due to torsion. Okay, that is one type of failure. Understood? That we must prevent. What other type of failures are present there? That is what we are looking for. Now see this part here. This is the you can say pulley is very heavy, let's say, and this side also pulley is heavier. And see, ultimately what they are asking, determine the diameter. Okay, shaft diameter. So if your diameter is very small, okay, we are supporting it here, and these pulleys are very heavy, then what will happen? Okay, so this, just a minute, wait. So you see, this is going to bend in this manner, isn't it? Because pulleys are pulling it, this pulley is coming down, this is, I mean, due to gravity, okay, their own weight is there, that is going to pull it down. Okay, this may not happen, no problem, but still, you see, we had two forces this sides, right? So P1, P2, this is P3, P4. Okay, consider only this part. Okay, now P1 plus P2, they are together downwards. Okay, they will have some effect together. P1 plus P2, that is pulling the whole thing downward. Okay, like this. All right, if we have the weight of the pulley also, then we if we have the weight of the pulley, then we have to add the weight also. If it is not given in the question, then you neglect the weight. Okay, so this is the total force pulling the pulley downward. Alright, understood? Okay, so that is the total force which is trying to pull the whole thing downward. Okay, so that will be passing through the center of this pulley, so that is causing some bending in this manner. Okay, understood? Okay, that is a force, and that force will cause some bending, and therefore there will be some bending moment. Okay, now this force is not downward. See, P3 and P4, they are in some different direction, like this. Understood? So if you combine P3 plus P4, this pulley is being pulled in this direction and this direction, so combined effect will be like this. Here combined effect will be downward. Okay, so ultimately from the observation, your shaft is going, initial shaft is, let's draw it again, one initial shaft. So this is the initial shaft, and final bending will be taking place. This is going down. Okay, this part is going down, and that part is going sideways. Okay, that side, I mean, not this much, but for understanding purpose, this is going down. Okay, and this is going that side. This is the bending happening. Okay, you may have understood this. So like this. Okay, so this is going inside the plane here. Okay, and this is downward. Okay, so there are two planes. Let me show you the planes. This is the plane which is vertical. It is vertically going downward. This is the plane which is horizontal, and it is going that side, bending in that direction. So there are two bending planes. Understood? And since there are two bending planes, we have to draw bending moment diagram of in two different planes. Okay, we cannot we can combine them later, but we cannot draw it in one single BMD, okay, at a time. I mean, sorry, simultaneously. I mean, we have to draw them separately, then we can combine them. Okay, so bending moment diagrams and shear force diagrams, SFD and BMD, these are the concepts we have learned in your strength of material. Okay, but I'll just still tell you a little bit about that. So this is what we have to do. Here we have to find out the bending moment. From bending moment diagram, we will get the bending moment, that is MB. Understood? Now see, since this is bending in this direction, so bending moment is there for this plane. There will be another bending moment for this plane also. Okay, but simply you have to find out the maximum bending stress. Okay, maximum allowable bending stress, that is sigma max B maximum. For that you need bending moment which is maximum. Okay, multiplied by y bar by I. So this maximum bending moment you have to find out from these diagrams. Now there will be some, I mean, see, from bending moment diagram, if it is not constant, if it is varying, then there will be a maximum point and maximum value. So from this we will get a maximum value. Okay, from this plane also we will get a maximum value, but we cannot compare because they are in different planes. So for that, what you have to do, we have to combine these two bending moments. Okay, so simply combination of any you can say, how do we combine is, let's say we have two forces, P1 in this direction, P2 in this direction. So any vector quantity can be, their resultants can be found like P1 square plus P2 square plus 2 P1 P2 cos of theta. Okay, so this is the formula. So you see, resultant of these two. Now see, resultant bending moment of these two, since they are vertical, they are 90 degrees apart. So this angle here also, this angle theta is 90 degrees, right? Okay, so when you put cos theta as 90 degree, that is 0. Okay, so 2 P1 P2, this term goes away. When you put theta is equal to 0, this term is not there, then this will be just P1 square plus P2 square. Similarly for bending moments also, if you combine the maximum or all the values of bending moments at each and every point, then the resultant bending moment, that is resultant only, is equal to root over bending moment in horizontal plane, vertical plane square plus horizontal plane square. Understood? So this is the way of combining them. So we have to just, whatever I said till now, we'll follow these steps, and finally we'll have to get this bending moment, maximum bending moment. Okay, and then we have to we already get this torsional moment. Okay, now you see that from the theory of your this one shaft, okay, we had actually just a moment, let me show you the theory. So from the theory of shaft, we have learned that the strength basis design for the shafts can be done by using maximum shear stress theory. So look at this. Okay, so see, shaft design on strength basis is, what we have to do is, look at this, we have to find out the this one by applying maximum shear stress theory. Is it visible? Yes. So equations can be written, and this is the equation that we have to use here. Okay, fine. So maximum bending moment you find out, maximum torsional, this is actually always since torque is applied to the shaft itself, so you will have only one torsion. Okay, the torsional moment. So maximum bending moment from the bending moment diagrams by combining and then finding out the maximum, plus this is square plus the torsional moment square, okay, multiplied by 16 divided by pi d cube, and this tau max is actually the allowable shear stress, allowable maximum shear stress, which can be found by dividing the failure stress, okay, failure, that is strength, okay, if it is yielding, yield is only given, so normally we consider the yielding only. What is the question? Yeah, only yield strength is given, so this is the failure stress divided by factor of safety will give you the allowable shear stress. Understood? So this is the way of finding out. So once you get tau max, you will at the beginning only you'll find it out, you'll find out MB and MT, and then from here we can find out the diameter. Okay, this is the design of shaft from on strength basis, and it is, and if they are asking you to find out sub design on torsional rigidity basis, that is Z into J value, then we have to use this, okay, twisting. I mean, we are not allowing the twisting to happen, okay. So okay, so this will come to I mean, we'll solve another numerical like this, but we'll first let me tell you about this numerical first. Okay, now look at this, look at the steps. Okay, let me use the red one only. Okay, okay, so look at this. Now these are the given things. SYT is given, okay, factor safety, belt drive, maximum tension. This is one thing that is given. See, maximum tension in the belt on the pulley B is 2.5 kilonewton. That means 2500 2.5 into 1000, that is 250. Yeah, 250. Sorry, this will be 2500 newton. So 2500 newton, okay, is the maximum tension in the belt drive. Okay, belt drive of your pulley B. So maximum and minimum. Maximum here is there. They are actually telling about your tight side tension. Tight side tension is maximum, okay, and slack side is minimum. I have shown you here. Look at this. Okay, tight side is more than slack side. Okay, so tight side is the maximum tension, then minimum. I mean, this can be termed as maximum minimum tensions. There are two tensions only, maximum minimum. So in maximum tension in pulley B is, that is P1 only. Okay, we can take it as P1. Okay, then angle of wrap. Oh, by the way, I'm not told you about the angle of wrap and all. So this pulley this belt is being wrapped around the pulley. Okay, fine. All right. So here you see, from this point and starting from up to this point here and this point, we have this pulley is being wrapped by this belt. Understood? Okay. Now from here it has started touching the pulley. This belt is, from here, this point it has been separated. There also there is a point that from where it will separate. It will get separated from the pulley. From here it has connected. This surface is touching the pulley. So here this is called the angle of wrap. Where is the this from here to that point, other point. This is complete. This is called angle of wrap. Okay, so this is not this is obviously less than 360 degree. If it is 360 degree, then complete wrapping is there, but this is not completely wrapped around. Okay, so this is required actually, angle of wrap. So here you have understood that. Okay, now